Okay, the next speaker is Jon Kleinberg from Cornell. Again, for those who are not here in the morning, I'm not going to read their long CVs, just tell you just very briefly a couple of highlights. With Jon, I don't know how many of you are familiar with his paper on the Hits algorithm or hubs and authorities. I don't know if he considers it a mistake that he published it rather than make a company out of it, but you probably know which company using a similar algorithm that actually references his, the PageRank, is doing well. The next paper he wrote, or shortly after he wrote this paper on 6 degrees of separation that I'm sure many of you have seen, and started his long interest in computational phenomena in social environments, in the social sciences, and that's what he'll talk to us about. Jon also wrote 2 books. One is a wonderful textbook on algorithm design with Eva Tardosh, and he wrote a book about the topics he'll talk to us about today on networks, crowds, and markets. So welcome, Jon Kleinberg.
Okay, thanks very much. Everyone can hear me? That's okay? Thanks very much, Avi, for organizing this really interesting event, and for the invitation to take part in it, and for the kind introduction. And it was a pleasure getting to see the talks in the morning, and also just to think about the themes that start to come together as we think about how computation is a way of thinking about issues across many different sciences. And when I think about the particular thing that I want to talk about here, the ways in which computation interacts with human beings, this too has a very long history. And as it's sort of becoming a tradition in these talks, I'll start with the same photo, but you know, if you think about the ways in which computation has interacted with people, of course, we've already heard in the morning some of the ways in which Turing thought about the interactions between computers and people. Obviously, the Turing test is one strong example of that, although the Turing machine is actually a second, in that it was, in a sense, patterned on the act of somebody actually performing computations laboriously by hand. And we saw a number of other, you know, as computing evolved, you know, we began to think about people matching wits against computers, Kasparov versus a very early incarnation of Deep Blue in that photo. You can tell by the low-tech monitor that it has there. And then, as time went on, we entered the 1990s, and things changed again. And this was sort of the phase when I was entering graduate school. It's sort of interesting to enter grad school at a point in time when your field is undergoing this radical transformation, because that was the beginnings of the web. The early 1990s was a sudden outpouring of information, human self-expression, and all the creative output of people being put online and being shared. And I think if you had asked, you know, me or my friends in grad school, or really anyone in the field in 1993, what is your working metaphor for the web? You know, how is this changing computing? We would have, you know, mentioned some picture like this. This kind of vast universal library of all human knowledge, right? Human knowledge was being put online, and we could sort of dip into it, and we could search it, and we could find what we were looking for. And that was already a very compelling picture, but even that picture got enriched roughly 10 years into the evolution of the web. This period, 2004 to 2006, when you sort of had a series of speciation events in which new kinds of things were created. In effect, people began to step out from behind their web pages and interact more directly, right? And so we moved from the metaphor of the library to the metaphor of the crowd, right? This teeming, dynamic mass of people who reacted in real time to events as they happened, such that you really had to assemble events now out of this composite of millions of individual perspectives, right? That the computational task now became this bottom-up inducing of some higher level structure. And it was really in this 2004, 2006 period that you saw the rise of Facebook, Wikipedia, YouTube, Twitter 1 year later. This is sort of all what happened there. And all through that two decades of progression, from the web and web search through social media, through people interacting directly, there was a sense that something new was emerging, something that wasn't entirely under our control, right? Something that we often feel when we have computational creations. It was expressed in a variety of ways. One compelling quote from the late Jim Gray in his Turing Award address, that the emergence of cyberspace and the web feels like the discovery of a new continent, right? That we're discovering something new, that we're getting more out of it than we put in. And I think there's sort of two things wrapped up in quotes like that. One is the idea that the online world is a phenomenon to be studied, right? That we're going to have to understand it on its own terms. And so in the running theme for the day, this is really going to be about taking the computational lens, right, computation as a way of looking at things and turning it on ourselves. And not just ourselves as economic entities or biological or physiological beings, but ourselves in our everyday, the mundane facts of our everyday lives, right? Even that is now something that we can think about computational, right? Your day-to-day experience of living your life is something that becomes something we can look at computationally because all of that, so much of it is taking place online. And there's a second point here, I think, which is that these online social systems live in this interesting intermediate state, right, these computational systems that we've designed, between the organic and the designed. And the point is, I think, if one talks to computer scientists, or if one talked to computer scientists in the early 2000s about the building of big social media systems, you have to remind them that these aren't like other information systems that you design, where you write the code and you check for bugs and you make it fault tolerant, but fundamentally it's going to do what you intended it if you didn't make a mistake. These systems have big human audiences, and big human audiences follow social principles of their own, and the system can kind of rebound in unexpected ways when you try to have things happen. And we saw some of that in Tim's talk, for example, with the unexpected consequences of creating incentive systems, and we see that in a lot of social design problems. On the other hand, if you approach this from the other direction, you think of these systems as really just big organic systems, right? These are human beings in their natural state interacting, and we get to observe it. Then you're going to be surprised by the opposite fact, which is that there is a big dose of design in these systems, right? So a system like Facebook, for example, and when I talk about some of the subsequent work I've been doing with my colleague Lars Backstrom at Facebook, Lars is the manager of the newsfeed ranking group there, and Lars and his team are essentially running a gigantic algorithm that's determining how to show you things in your newsfeed that will be maximally engaging to you. And so when you go on Facebook and you experience it, you're not experiencing a kind of default vanilla system. You're experiencing one that's been designed and being optimized for things like engagement. So it exists on this knife edge, partly organic, partly designed. And what we'd like to think about is, what does that kind of a world look like? What's the terrain of that world? And the terrain is made up of a number of things, right? There's heavy doses of geography, a lot of social principles that I'll talk about, and it's also graph theoretic. And I think that this was another way in which computer science is sort of imposing, part of its perspective on these systems, that long history of thinking about graphs as one of the essential substrates of computation. And graphs have really been adopted incredibly powerfully as a metaphor in the online world, such that when I first began teaching about this in undergrad classes a long time ago, you sort of had to explain what the dots and the lines were. And now, in a way, this is just part of the metaphors that we use, right? So that something like political polarization on the left there becomes this striking picture drawn by Lada Adamik and Natalie Glantz just before the 2004 US presidential election, of all these left-wing bloggers over there in blue on the left and all these right-wing bloggers on the right, forming two dense clusters in the graph and not necessarily connecting across to each other. Or, for example, political mobilization, as in this anti-war chain letter that David Libanel and I began studying a half year before the US invasion of Iraq in fall 2002, and ultimately 6 years later wrote a paper about. It becomes this branching tree as people recruit others to join the cause, and you see this tree-like structure branching out through the social network. So all of these systems are really shot through with graphs with quite complex structures. And if we want to understand what the online world looks like, in a way it becomes a sort of mapping exercise, right? A conceptual mapping exercise in which we would like to take, these are relatively modest-sized pieces, but we ultimately would like to understand, what does the social network of the world look like? And can we, from this computational perspective, understand what it looks like as people go about their everyday lives in these social networks? There's sort of I'll try to stick to the mapping metaphor here a few times. There's something sort of different about mapping these networks, obviously, than mapping the physical world. And part of it is to figure out what are the ingredients that go into all of this. Part of it is also, as with mapping the physical world, although we've gotten used to that one, there's this notion of maybe the shock of the familiar, right? The idea that we're seeing things that we see in our everyday lives, political polarization, word-of-mouth effects, but we're seeing them cast in these new ways through these graph structures, right? Looked at through algorithms with massive amounts of data. And sometimes when I think about what it looks like when an algorithm is looking at a massive social data set, such as it would in blogging or in Facebook, you think about this intelligence very different from our own, right? This sort of alien intelligence off to the side with massive data sets, able to detect very subtle patterns, but knowing nothing about everyday life, right? And that's, in effect, what these massive algorithms that Facebook and Google are doing. They have, only the domain knowledge, the limited domain knowledge you might put in, and they're inducing most of it otherwise from the data itself, right? They are sort of like these Martians sort of observing us and seeing what they can find out. And it's sort of interesting to ask, what is it that aliens would learn just sort of looking from the outside at what's going on? Would we recognize it? Would it be meaningful? And actually in that, I was, sort of my colleagues and I were, began to get into this metaphor, and I began to realize that I actually heard this metaphor before, and where I had heard it actually was because of this paper. When I graduated from college, the spring I graduated from college from Cornell in 1993, Carl Sagan was giving a lecture on campus, and Carl Sagan was a much beloved figure among Cornell undergrads. This was shortly before he passed away in 1995. And on the other hand, Carl Sagan's sightings on campus were often kind of rare because he traveled a lot and he was a celebrity. So when he was giving a lecture, that was interesting news. His lecture was entitled, "Is There Life on Earth?" Which was not what we kind of, not quite sure what to make of that. So we went, and actually it was based on this paper in Nature, and Nature had put the same question on its cover, right? This is only a slightly more comprehensible title, "A Search for Life on Earth from the Galileo Spacecraft." You see, what had happened was that one of these exobiology things that they were doing, they launched a space probe into the outer solar system, and as these things go, you first have to kind of slingshot it through the inner solar system, and it came back out. And as it did it actually passed over the Earth with its formidable array of measurements, and it turned them all on the Earth, and then it went on. And what Carl Sagan and his team here said was, as a kind of good sanity check on the planet, if the planets find weak signals of life on Mars or on the moons of Jupiter or Saturn, at the very least, it would be kind of reassuring if we could detect evidence of life on Earth as we pass over. That was the hope. And so he gave this 1-hour lecture, and he said, let's pretend we're all Martian scientists. And we're looking at the readings coming off of Earth, and we want to understand, what's unusual here, what might jump out at us. And, I don't recall the whole lecture anymore, but, there were certain clearly unusual things about Earth, the balance of diatomic oxygen with a whole bunch of things that should be combusting in diatomic oxygen, and means there's something else that's replenishing diatomic oxygen. And you see, you sort of start from some of these unusual things, and you go from there. Now, when I think of the metaphor of Martian scientists, the emissions coming off the Earth are not so much physical and chemical, they're more digital. They're the digital traces that we all leave in the going about of our everyday lives. And we'd like to know, what is it that just inducing from the raw data that we might see. Just as an example of this, and also just because it gives some intuition, there are some cases where you can look at something and say, is it meaningful or is it not meaningful? One kind of life on Earth experiment that I did a few years ago with Dan Huttenlocher, Lars Backstrom, and Dave Crandall was to look at big photo sharing sites. So you upload photos, and if your camera has a GPS or you use the map interface, then you're going to give you're going to get the latitude and longitude of the point from which this photo was uploaded. And so you can take 100 million of these, each with a very, very specific latitude and longitude. And you could put them as sort of a first step in processing all of this data. You could put them on just a black screen like that, right? So we have a black screen here, but now I'm going to put a white dot at the exact latitude and longitude of anywhere where a photo was uploaded. All right? And you could ask, if I do this, shapes will start to appear, and are these shapes going to have any meaning? Am I going to recognize anything? And the point is it's fairly recognizable. And I want to actually draw attention to a couple things, because as we enter domains where the data is less intuitive to us, it might help to remember the heuristics that we use in making sense of this picture, right? Because, again, the fact that there's a map here is only in your own imagination, so it's just a bunch of white dots on a black screen. But it's clear the dots pile up in certain places, at certain population centers, cities, and so forth. There's also, of course, dark regions, this region which is strangely black for reasons I'll let you figure out, and, this big ocean here, and so forth. And we should remember, of course, that a couple of things. One is when you see a blank region, it could be for two possible reasons. It could be because you can't live there, right? No one really lives out here. I mean, yes, when you're flying in a plane, you might take a picture and upload it, so there are a few dots. But basically, people can't live here. But then this was actually Flickr, was the photo site we used. There are also places where people just, aren't on Flickr. So here, there's a lot of people here. They're just not on Flickr. And so there's a question of, can't live there versus don't live there among the population of Flickr users. And we should remember there's sort of two reasons why the space might be empty. We should also, sometimes there aren't just dots, but there are these one-dimensional threads, right? Like a river or, a place where affluent Western tourists go and climb high mountains and take pictures of them, things like that. These sort of one-dimensional threads through the data, and we should ask, what do those mean? And all of these are fair game for when we try doing the mapping of more complicated things that we don't really have this intuitive understanding for, right? This is a kind of nice sanity check because we know what the surface of the Eastern Hemisphere is supposed to look like. So when we want to go map social networks, right, if we want to ask the question, what does the social network of the world look like, we should know something about what the building blocks are. And the field of sociology gives us 100 years or more of basic principles here, which are actually quite useful, right? How are social networks organized in everyday life? And I'll call attention to a couple things, right? So there's long lines of work on, for example, the principle of homophily, right? The fact that when we have basic characteristics in common, that tends to guide who we form links to. We link to others who are like ourselves. Sort of the opposite of homophily, the declaring of others as the other, leading to polarization, conflict, things like the theory of structural balance. And then just in the global organization, I'll just mention two things here that will come up later on in the talk. One is one of the most recurring regularities of social networks in everyday life, which is the principle of triadic closure. That if I have someone A and they have friends B and C, then there's a greatly elevated chance that B and C are going to form a link at some point in the future. For all sorts of reasons, right? A may have an incentive to introduce them. B and C, at least we know, travel in similar circles. If they both know A, they might just meet each other. And homophily says that if B and C are linked to A, they may have some latent similarity. A next step beyond homophily is this notion made famous by the sociologist Mark Granovetter of strong and weak ties. And in effect, the theory of strong and weak ties suggests that we think of social networks as having these dense clusters around, particular strongly knit social groups with other links between them that are weaker, that span between groups. Okay? And so the idea that even if I just look at an unweighted graph of the social network, it's inhomogeneous in the sense that certain links are weak, they're sort of distant acquaintances who you don't see very often, and certain links are strong, they're people that you see every day. And triangles are somehow intimately wrapped up with that, because inside these dense clusters, you have lots of triangles, and the places where the triangles have somehow failed to form are often where the weak ties are. Okay, so triangles closing, dense clusters, these are sort of useful raw materials for thinking about this. This all takes place at a local structure, right? Homophily is about the forming of a link between two people, triadic closure among three people, these among small groups. What if we, let's keep coming back to the question, let's keep pushing on this question, what does the social network of the entire world look like? Now, the first person to actually sort of attempt to study this, well, it's hard to pin down the first. One of the most high-profile early studies of this was Stanley Milgram's 6 degrees experiment, which Avi mentioned in his introduction. I wanted to spend a couple slides just harking back to that, because in a sense it is sort of, maybe the first well-known attempt to say, let's stop looking at small groups and start looking at the social network of the entire world. And also it might say something about some of how I became interested in this and tried to start building computational models for these things. So what did Stanley Milgram try doing? So he was inspired by these ideas in popular culture that were all a small number of steps apart. And this was partly anecdotal. You actually find it in fiction. The relatively well-known Hungarian short story writer Frigyes Karinthy actually wrote a story in the 1920s in which a bunch of characters sit around speculating about how many links it would take to connect themselves to famous athletes, the CEO of Ford Motor Corporation, things like that, right? And so there was this idea in the air, but no one had tested it empirically. I mean, how could you, right? So this is now the 1960s, and Stanley Milgram gets a grant, $680 to test this. So sort of not quite the, and so he had no big data resources. He had this budget of $680 that would cover, postage. And he decided to do this just by doing some experiments through the mail. So he did the following. he asked a friend of his in Sharon, Massachusetts, a suburb of Boston, would you be my accomplice in this? I would like people to try building chains to you. And he picked 200 people at random in Nebraska, because he said from his position at Harvard that just felt kind of far enough out there that it would be a fair test. That's more or less what the paper says verbatim. So 200 people, and he sends them all a letter and says, we're doing this study. We're trying to see if we're all linked together in the world. Here's this person I would like you to find in the U.S. And they're in Sharon, Massachusetts. Here's their name, their address. Here's their occupation, where they went to college, their wife's name, a bunch of things. They were in the military. But you can't just mail the letter to them. That would be a test of the U.S. postal system, but not what he's trying to test here. You should mail it to someone you know on a first-name basis with the goal of advancing this letter eventually toward the goal. And so, you think about it, you're in Nebraska. You're like, I have to get to this. This person was a stockbroker. So I could mail it to someone I know who's a banker. I could mail it to someone I know who lives in the Northeast. I could do a bunch of things, but I'm trying to get it closer to this person. And the amazing thing that happened was, compared to, future replications of this experiment or other attempts to do these things, participation in this was very, very high. The attrition at every step was they only lost about a quarter of the people every time. And so, out of the 200 started, roughly a third made it. They zeroed in across the country. This is actually Milgram's hand-drawn picture in his paper showing the kind of average collapsing. It's sort of shrinking by half every time. And the median number of steps, I should say median, not average, was 6, this number that John Guare then injected into pop culture through his play, The 6 Degrees of Separation. So that was the experiment. And it was a striking experiment, partly in sort of audacity, right, that he didn't collect a big data set. He didn't have any resources. He just mailed 200 people letters and said, help me out here and let's see what happens. And we got this very, very striking finding. And what struck me about it, looking back, was, so this experiment was sort of known in the sociology world. It got an enormous amount of attention focused on it thanks to the work of two of my colleagues who were then both at Cornell, Steve Strogatz, who is still in the math department at Cornell, and his then PhD student, Duncan Watts. And they proposed some models for what they called small world networks, right? Networks where you would have this kind of short path property. And that was how I encountered it. I'd been thinking about web search and the problem of search in general. They were thinking about small world networks. And there was a search problem in here. And in some sense, maybe to a computer scientist, it's obvious that there's a search problem, even if that hadn't been the focus of attention thus far, because it wasn't just that the paths were short. Because Milgram had been operating under such enormous constraints in how he could set up this experiment, right? He didn't have the email graph of the world. He didn't have the Facebook graph. He couldn't just compute breadth first search. He had to have all these people helping tunnel their way through the network. He was basically asking people to do a much more interesting task, a distributed routing task, right? Where you say, I have this letter. I don't have the map of the network. I know I'm trying to get to this faraway person. I need to figure out who to send it to with the best chance of advancing it toward the goal. And so somehow we actually learned a second thing about the social network of the world. Not just that the short paths were there, but that they're actually findable, right? That the knowledge is somehow collectively in the network that you can actually tunnel your way through and in a short number of steps without a map get to the target, right? It didn't have to be that way. You can build networks which have the first property, short paths, without the second property, navigability. So that turned out to be something you could actually ask in a precise way, and I'll just spend 2 slides on this before popping back up from older history. But that was the question, right? Routing in a social network, when is this local information sufficient, right? These people who started in Nebraska had to make guesses where to send a letter, didn't have a map. And what was interesting was that the Watts-Strogatz model was actually a very nice model for asking this question in a precise way. Because effectively, to scramble their model slightly and just draw it here, it was a model that was actually built from these social network principles, from homophily, from strong ties versus weak ties, from triangles. It basically said, imagine that there's a lot of geographic homophily in the world. Everybody tends to know people who live close to them, right? So if it starts in Nebraska, you know a lot of other people in Nebraska, and you know fewer people in the Northeast US, right? So imagine in this abstract model that we have a grid, and people know each other within some radius on the grid. But then there are these world-spanning weak ties, which are what make the world small, right? These red links. And maybe what we'll do is take the grid and we'll just add things at random. So node U will link to node V with probably decaying in their distance, right? So their grid distance is going to be called d of uv. The probability that U links to V is going to fall off like d of uv to the minus alpha for some alpha that I can tune. Okay? So I have basically this one-dimensional family of models. It's a grid with red edges. And by turning alpha as a dial, I can make the red edges be very long and random as alpha goes to 0. or as alpha goes to infinity, the red edges collapse to become very, very short. Okay. And now I could say, all right, people, if someone in the upper right is trying to get to upper left is trying to get to someone in the lower right, we're trying to get from Seattle to Miami on this grid, and everyone knows the grid, but they don't know the long-range red links. They only encounter them as they get to the person, right? You know who your long-range friends are, but the other people don't. And that's the decentralized aspect of it. That's the distributed routing aspect. And what turned out to be the case, you could prove some things about this model, that there was an optimal exponent for search, which was neither too big nor too small. It was actually the dimension of the grid. So in my two-dimensional picture, it's alpha equals 2. Okay, and that's balanced between smaller values of alpha, where there are lots of short paths, but you provably can't find them with reasonable probability, and larger values of alpha, where they're just, the paths just get longer and longer, and even if you could find them, they're not useful. So this was an interesting model. It was fun to play with, but I somehow got out of it a prediction that was much more specific than I had intended to have, right? So I end up in the situation where there's actually a prediction, alpha equals 2, which was, a sort of surprisingly specific prediction for such a simple model. And, people ask me, so is this right? And I sort of hedged, I'm like, this is a very simple model. It's sort of saying that there's some intermediate thing here, but, who knows if it's really 2? Who knows what alpha even really means in real data? And besides, in 2000, I said, how would you ever test this? You would somehow need a system where for some reason you could somehow convince millions and millions of people to voluntarily sign on, say where they lived, and say who their friends are, right? And when is that ever going to happen, right? And that happened very quickly, and we get these online social networking sites, and it was really a bunch of my colleagues in the Bay Area, Prabhakar Raghavan, Andrew Tompkins, Ravi Kumar, Jasmine Novak, and a former student of mine, David Libin-Nowell, who had this insight that, wait a minute, we've got friends and zip codes. Let's actually try to measure what the exponent is, right? And so I sort of felt on the hook sort of for this prediction and how it would turn out. Now, it turns out if you're going to actually do this on the social network of the world, or the US in the case of these social networking systems, the model, okay, we don't all live on a grid, we don't all have links to fixed radius, so forth, so on. You can make all those go away. You can generalize the model quite a bit. Maybe the hardest one to make go away, surprisingly, is the fact that the population density is so non-uniform. And you can imagine ways of stretching and shrinking space to make it look uniform like it does on the grid, because that was essential to the alpha equals 2. But the easiest way to stretch and shrink it is actually ordinally. So here's a different way to talk about probability decaying with distance. Don't think about actual distance. Instead, each node is going to rank all the others by closeness. Okay? So the rank of W with respect to V is the number of nodes that are closer to V than W is. And now we'll say that where I had the inverse square law, what does that mean in rank? Well, here's V. Consider someone at distance d. You draw a circle of radius d. There are about d squared people inside. So at distance d, the rank is d squared. So 1 over d squared is 1 over rank. And so the short story here is, if you want to generalize 1 over d squared as the linkage rule to arbitrary distributions, 1 over rank is one way to do that. Now we can go in and actually look at data from online social networks. And again, this was first done by David Libin-Nowell and his co-authors on a set of networks that at this point mainly have archaeological significance more than anything else, things like LiveJournal. And they got this number that was actually surprisingly close to 1 over rank to the 1.05 if you restrict to the two coasts. And this was then done by a number of people, Lars Backstrom and some co-authors, 5 years later with Facebook with enormously greater data density. And again, you get 1 over rank to the 0.95. Sort of a surprising way in which this number that came out of an extremely toy model that you can play with and prove theorems about ends up showing up even once you actually collect all this data and you actually compute something. And with that, of course, there's simply a new question, which still remains sort of a mystery, which is this is the optimal configuration for search. But all of us forming links in our everyday lives are not trying to optimize our networks collectively for the Milgram experiment. That's not what we're trying to do. We're trying to do a whole bunch of other things. We're trying to make friends, meet people, find jobs, find a new apartment, and so forth. We're doing lots of things. The Milgram experiment is just somehow this byproduct. And so what is the selective pressure on the network that is somehow driving it toward this optimal operating point for this particular task? And that is an interesting sort of open question where there's a lot more modeling work that one could imagine doing. But this was a story which, from my first involvement in it till this data began turning out was 1 decade long. If you reach back to the Milgram experiment was 4 decades long. Began with someone doing an experiment with pencil and paper and postage stamps, a very sophisticated experiment, ends with a billion-node network and the investment of huge amounts of resources, but is sort of fundamentally asking a consistent question through the whole thing, which is, what does the social network of the world look like? And so what I want to talk about was some of the things that we've been looking at as we try to go deeper into these social networks. Because if I think about what you might do after that point, the problem is that it is just very hard to think about these networks, right? So navigability turned out to be one nice direction along which to ask questions. But in some sense, if you really think about the billion-node Facebook graph, then in any real sense, it is incomprehensible to us as human beings. We can't think about billion-node graphs. And the fact that most pairs of nodes in that billion-node graph are 6 degrees or fewer apart, it's actually slightly fewer, only makes it worse. Because it says the network is some gigantic, almost sort of uniform metric on everybody. It's just very hard to see how we're going to get leverage on it. So one thing that we've been looking at recently, and here I'll talk about some work with, again, Lars Backstrom, former PhD student of mine who, as I mentioned, manages newsfeed ranking at Facebook, and Johan Ugander, who just finished his PhD with me and now via a postdoc at Microsoft is going to be starting a faculty position at Stanford MSD. The three of us thought about looking at the network in a sort of different way. Take the Facebook graph and say, we have this very complicated mathematical object. We can't understand it globally. Let's localize around individual points. Okay? So let's take each node and let's think about what the neighborhood of that node looks like. Right? So you and your set of friends, that's a graph just out to radius 1. And we could think about Facebook not as a billion-node graph, but as a collection of a billion of those. Right? There's you and your friends, and each of us has one of those shapes around us. And we could ask, what are the common properties of those shapes, and then try to sort of think about how the graph is pasted together from all of those. So if we think about what one of those looks like, let me show you an example, because actually it's useful for intuition just to see what they look like. So this is a Facebook engineer at the center who basically donated his network to science that we could look at here. And these are all his friends. And so the nodes here are friends of this guy. And there's a link between any two who are friends with each other. And the interesting thing is, Lars and Johan and I have, now stared at hundreds of these things. And in some sense, they all look very, very similar. This is what if you've ever mapped your own friend network, you would see something like this. And in a way, almost, like any aesthetically compelling, profoundly aesthetically compelling thing that certainly we found it so, if you look back at it over a couple of years, you come back and you see things you didn't see before, and that's happened to us a couple times. So what are we seeing here? So there are these dense clusters, right? So this is one part of this guy's life, and this is a different part of this guy's life. These are actually his coworkers at Facebook. These are his old friends from college. Somewhere in here is his extended family, which is in one of these clusters. There are some other clusters, a hobby maybe, some other thing he's doing. They're just sort of these things, and all of us have that, because if you think about it, take your own personal friendship network and take your coworkers and take your old friends from school, the people you grew up with, your family. The only thing they have in common is you. Right? You're the only reason this thing is all being drawn together. And so you are at that intersection point. Right? And, and you see all the things that Mark Granovetter sketched in his influential paper on the strength of weak ties, right? The strong ties within here, the weak ties that span between clusters. All of that is present in this picture. So that was our starting point. Think of Facebook as a billion of these. And if we think of Facebook as a billion of these, can we map the network in some kind of different way? Can we say, let's stop thinking about this as a billion-node graph and start thinking about it as some other object with some structure that we might be able to make sense of? Now, if we're going to ask, here's what this graph looks like, it's always good to ask, what should we have expected it to look like? And a good baseline, whenever you ask, what should I have expected a graph to look like, is actually to go back, long before the Watt-Strogatz model talked about randomness on a grid, a much simpler model, the Erdős-Rényi random graph model, known as GNP, which is the simplest thing you would do if someone told you, create a random graph on n nodes. You would put down n nodes, and for each pair of them, you would flip a coin with bias p independently. And if it comes up heads, you'd put an edge. Okay. Now, in terms of, as a model of real life, GNP has a number of well-documented deficiencies, and we shouldn't blame the GNP model. After all, Erdős and Rényi made it up, as an interesting object in itself, and to prove existence results in combinatorics. But it is the case that, if we think about GNP, first of all, it doesn't produce high variation in the number of neighbors. So if you're trying to model something like the web graph, it has the problem that the web graph has very big node degree disparities, and this doesn't. That's less of a problem for us because we're looking at social networks where the degrees are more uniform. Maybe a bigger problem for us is, let's go back to triadic closure. Real social networks are very rich in triangles for the reasons we've been discussing, whereas GNP doesn't care about triangles, right? The probability that these three edges all appear is p cubed. They're all independent. There's no special bonus for being a triangle. Right? Whereas in real life, you'd see this fill in, you'd see that fill in, you'd see a bunch of triangles. Okay, so that's going to just be a useful baseline to think about. If we want to describe what we actually see, if it's not GNP, one thing we can do is actually draw on what's become a very richly developed branch of extremal graph theory with a lot of nice work, some of it done here as well as elsewhere. And the idea is to try to create a very thin set of coordinates for this set of graphs. Here's how I'm going to do that. So I'm going to pick some small value of k, and I'm thinking very small, k equals 3, k equals 4. And so for every possible k-node graph h, we'll say f sub g of h, g is my big graph, my neighborhood graph here. F sub g of h is the fraction of k-node sets that induce a copy of h. Okay? Now, this has a long history. It actually, this too links into old work in sociology, this thing called the triad census proposed by David Leinhardt. It's shown up in computational biology as network motifs in the data mining community. And as I mentioned, this very, very nice work on graph homomorphisms that's developed the subject quite extensively. And we thought, would this be a useful way to characterize the neighborhoods that we see on a graph like Facebook? And so this is what Johan, Lars, and I thought to try doing. So if k equals 3, there are 4 possible graphs on 3 nodes. Here they are. And if I looked at these 3 nodes, maybe that edge is present, that one isn't, so it would add 1 to this. And I'd get some vector here, right? Some 4-dimensional vector describing this neighborhood. Obviously, there's a huge loss of information in doing that, but it's a thin coordinate system that might be useful. It actually is effectively 3-dimensional, because these 4 numbers add up to 1. So there's 3 degrees of freedom here. I could do it for 4. There are 11 graphs on 4 nodes. There's no reason you should actually know that, but there they are. And that's a 10-dimensional representation. Okay, so you could run through all the neighborhoods on Facebook, or you could fix some graph size and run through all the neighborhoods of that size on Facebook. And I basically have a 3-dimensional coordinate system for them now. So I could do the same thing I did with that map of the Earth, right? You start with a black screen, and you start putting dots every time you see an instance in the population. What would that look like here? I start with a blank screen. Now it's a cube, a 3-dimensional cube. This axis is the density of empty graphs. This axis is the density of triangles. And this axis is the density of floating edges, right? Just the one edge with the dot. And I've eliminated the wedge. That's the 4th degree of freedom, which I took out, which is redundant. Okay, what's the next thing we do? For every neighborhood on Facebook, you put a dot in the space where you actually see it. And I won't draw it for every neighborhood on Facebook, because after a few million of them, you start to get the idea. There's a shape that forms. You put them in, and you actually get this interesting shape. Okay, so now remember, this is a three-dimensional thing here, and unfortunately, I don't have a revolving cube picture for you to look at. But it basically, this is actually uses all 3 dimensions. It comes up and it has this sort of serpentine kind of torsion toward the back as it goes away from you. Now, what do we see with the map of the Earth? A few things to remember. Some population density and then some blank spaces. And when you see blank spaces, you should ask, is it blank because people can't live there, or just they don't happen to live there? Same thing is true of graphs. Some of this region is actually blank because mathematically graphs simply can't do that, right? So for example, it's just a theorem in extremal graph theory that you cannot have a graph where more than 3/4 of the 3-node sets induce this thing. Right? I could have a graph where everything induces a triangle, just make a complete graph. I could have a graph where everything induces the empty graph, just have no edges. But I can't have something where everything induces this. The best I can do is 3/4. So the whole top quarter of this cube is sheared off for a mathematical reason. But other parts of the cube are missing for social reasons. You could be here. You just sort of aren't. People don't form. Essentially, what's here and what's not being shown, except for these occasional outliers, is basically neighborhoods that are big, complete bipartite graphs. That's sort of the missing mass in this picture. Because what would that mean? It would mean you have your friends are organized into these 2 groups, right? Complete bipartite graph, edges all across. Your friends are organized in these 2 groups, and everyone in group A knows everyone in group B, but no one in group A knows each other, and no one in group B knows each other. It just doesn't happen, right? Human beings simply can't form network neighborhoods, or don't, that look like that. Okay, now you could ask, like, what's the full feasible region here? And that actually leads to some very, very hard questions in extremal graph theory. You could also, actually, there's one more bit of intuition we should remember. when something looks like a one-dimensional thread, you should ask, what is the river or the mountain range or the interstate highway that runs through that one-dimensional thread, right? Why are they following this track? And actually, as you go to bigger and bigger neighborhood sizes, this thing tightens up. And it gets thinner and thinner and looks more and more like a one-dimensional tube running through the space. And the river that's running through it is actually in this approximately GNP. So GNP in this space is a parametric cubic curve because the density of triangles is p cubed, the density of empty graphs is 1 minus p cubed, the density of that thing is 3p squared 1 minus p, and so forth, right? P times 1 minus p squared. So I have a parametric cubic curve through the space, and it actually looks like this. It too has this kind of serpentine torsion toward the back. It sort of misses the points here, and precisely because of triadic closure, right? The cloud of points is pushed to the back in the direction of too many triangles, right? That's exactly where GNP misses it. There's a lot more I can say about these shapes and some models that we've tried building for them. I won't have time to get into that here. Happy to discuss it afterwards. But this is, the beginnings of trying to map this out by looking at neighborhoods and then trying to find a thin representation, right? It taps into some of Rezborov's pictures of what the feasible region looks like and so forth. Okay. Let me talk about an application that we looked at, right? So once we have neighborhoods, once you think about the graph as neighborhoods, what can you do with these neighborhoods? Well, what would you want to do with these neighborhoods? So one thing to think about social neighborhoods, right? Again, as we try to zero in on what does the social network really look like. In a Facebook context, when Lars and I were thinking about what does this mean for what he does day in and day out, which is prioritize content for people's news feeds, the neighborhood is sort of the input to the core problem that Facebook is trying to solve in sharing content with you, right? You log into Facebook and you're sitting there at the center of your network neighborhood. Your friends are generating lots and lots of content, right? The posts and the photo shares, the link shares, the check-ins, the invites, the likes, the comments, the song listens, all that stuff is this fire hose of things. There's roughly 1,000 to 2,000 pieces of content that your friends generate per day if you put all that together, right? That's about 10 times the size of a busy inbox, a busy email inbox. It's too much for you to consume. There's inherently a ranking problem to figure out what to show you to have the sort of best experience, because showing it to you all is not the best experience. So there's a prioritization, and the input to that really is this social neighborhood graph. And there's lots of information that you want to use for trying to prioritize that, in which Lars and his group have optimized over a number of years about how much do you interact with this content, how much do you interact with these different types of content. But the network also plays some role in it, right? Because let's go back to strong ties and weak ties. There are some people where you really do want to know what they had for breakfast this morning and you want to see a photo of it because this is a very close friend, it's, a relative, it's something. And then there are a lot of people where you don't want to see that every day. What you would like to know is, kind of high-level events, like, if they get a new job, they get engaged, they have a baby. You'd like to hear about that. But you don't want to hear about every single thing, right? So there are these concentric layers around you based on strength of ties, strong versus weak ties, that govern how to prioritize the content. And if we had the network neighborhood and could somehow get leverage on this question of where are the important ties in there, that would be telling us something that would be relevant to this prioritization. Okay, so that's the question that we were asking. And this is a question that the whole theory of tie strength in sociology has asked over a number of years. Given a person's network neighborhood, can we identify their most significant social ties? Now, structurally, the way people have gone about this is this notion of embeddedness, which is intimately related to triadic closure. Right? Triadic closure is going to come in here again. So the embeddedness of an edge is the number of triangles it contains, or equivalently, maybe more intuitively, the number of mutual friends shared by E's endpoints. So here's a graph. Apologies for those of you blocked out by the podium there. Here's a graph, edge VW. They have 4 mutual friends. Okay? So VW, they got 4 friends in common. And the argument in the theory of tie strength is that the embeddedness is highly correlated with the strength of the tie, right? Tie strength is monotone in embeddedness. Because if you have a very close friendship with somebody, then over the course of your relationship, you will accumulate lots of mutual friends. And if you have someone you barely know, then there are fewer opportunities to accumulate mutual friends. And so conversely, if I see a link with very few mutual friends, I suspect you may not know that person very well. Okay, so embeddedness is sort of key to this whole theory to the extent that often embeddedness and tie strength are sort of wrapped up with each other. It's often in this whole area sort of hard to tell where one begins and the other ends. But they are distinct issues. Tie strength is what you would actually like to infer. Embeddedness is one implementation of how to go about inferring it. But it suggests a heuristic. What if we went back to those neighborhoods and we tried to rank all the neighbors by embeddedness and saw who were the strongest ties here? So Lars and I started looking at that a couple years ago. So let's go back to the Facebook engineer and all of their friends. And, ask what happens if you simply, this is the idea, we're going to rank all the friends by embeddedness, right, number of mutual friends. And we're going to look at the top and the next one and so forth and ask, are these really their best friends in the world? It's just a ranking measure. What happens, and somehow the instant you try it, you see what goes wrong with it, right? I mean, it sounds great, and it is, we'll see, it is a completely correct idea. It's not the whole story, because embeddedness, for example, here, and on most people you try it with, will find a whole bunch of nodes from just the largest cluster. Because what's going on up there? You've got like this guy and his 40 coworkers at Facebook, and it forms almost a giant clique. Actually, the answer to Tim's question is yes, there is a clique of 100 people on Facebook. They form this near clique. And so for any random coworker that you have at Facebook, you're going to have like 30 mutual friends. And if you were to ask the person at the center, is this one of your really close friends? They'd say, I mean, I know them, I work with them, they're not one of my best friends in the whole world. But, there's just huge embeddedness because everyone knows each other. And similarly, the old friends from college. Whereas, the family cluster down here, you've only got, an extended family of like 8, 10, 12 people. They just can't compete, right? So there's almost a currency conversion problem going on here where the value of a mutual friend here is just not the same as the value of a mutual friend here. The ranking is just not doing it. Again, this is not to say it's broken. We'll see in a couple slides that embeddedness is doing fine for itself, but it's missing something important. And we asked ourselves, can we sort of pin down more precisely what is it actually missing? And we went back to pictures like this. And as I said, with aesthetically compelling things like this, you come back and you see things you didn't see before. And we saw something begin to jump out at us that, should have jumped out at us right from the beginning. Maybe it jumped out at you right away, which is this node down there. This node is somehow, it's not quite competing with the embeddedness of the other nodes, but it looks very striking, right? It has these links out to all these different clusters going in all different directions. It's sort of there. It feels significant, right? It's different. This node is different from all the other ones that have similar embeddedness. It's something special about it. And you want to know, what is special about it. It turns out this is actually the spouse of the coworker center. Right? This actually is a very important person in the social network. And so we said, okay, there's something that we're missing here. And in a way, it's flying under the radar of embeddedness. We see it. Actually, at this point, it's worth remarking on, we saw it because what is this actually? This is a spring layout. So it's the optimization problem, embed the nodes in the plane. Each, this is going to be the second talk in a row that has springs with unit tension showing up in it. Embed the nodes in the plane. Each of these is a spring with fixed tension. And you want to then, subject to the centroid is here, the sum of the squared displacements is 1, and now minimize all the squared edge lengths. And this happens. And this thing really stands out, because there's just nowhere for this to go without stretching a bunch of springs. So we see it flying under the radar of embeddedness, what's going on. So, in the spirit of, I felt like, my training as a computer scientist says, when you encounter a problem that eludes your current techniques, then, make up a challenge problem that somehow encapsulates what is it the current techniques are not doing, so that if you can then go and try to solve that very concrete challenge problem, you'll be, in a sense, forced to make up some new technique. And that's what we did here. So we asked the question, given a Facebook user in a relationship, find their relationship partner from the pure network structure. Right? Not because we set out to solve the problem of finding relationship partners, although it's clearly a very intuitive question, but because it's something that the techniques were not doing. And if we could do this, then we would have had to have done something different. So a very concrete question. And again, I sort of promised that we would try to get to computational questions that are really about, the everyday facts of our day-to-day lives. Right? It's a very concrete question. This person has declared in their profile who their relationship partner is. And I give you the pure graph structure. And so it's a well-defined question, right? So like many of the questions I have enjoyed over the course of my life, it begins, the input is a graph G, but the output is find the one node who's relationship partner. Right? So the input is very concrete. The output is, we're not sure what the right thing to do is. Okay, so what should you do in a situation like this? Well, the fact that jumped out at us visually tells us something about where to start looking. And one thing is, obviously, embeddedness is an incredibly simple measure. It just says count mutual friends. But you can do lots of things besides counting mutual friends. You could also look at their internal structure. So, for example, here's V and W, here's V and W. In both cases, they have an embeddedness of 4, but for very different reasons. Right? This is sort of the coworker story, because they form a clique on 4 nodes. This is something else, because these two know each other, but they're somehow separate from this one, separate from that one. V and W here are acting as a kind of bridge between all those different groups. So somehow V and W jointly are what all these things have in common. Right? So in the same way that earlier I was arguing you are the only reason these things appear together. Now the two of you are the only reason these things appear together, right? And that says something significant about this VW relationship, right? Or to put it a different way, from V's point of view, there's no simple way to explain what cluster W belongs to, right? They're not one of your work friends, not one of your family members. They're between clusters. So it's a kind of, it goes back to some of the social network principles that I put on one of the opening slides. It's a kind of bridging. You're bridging between communities, but it's done jointly by V and W, and it somehow conveys tie strength. So once you have this idea, you could then try to make this concrete. You could make up a measure for it. And when you're trying to capture some kind of bridging role, it actually is useful to go back to degrees of separation and say, in effect, what a bridge is doing is it's reducing distances. So what you could say is, let's say C sub VW are the common neighbors of V and W. I could be interested, for example, in the sum of the distances among all the common neighbors, all the pairwise distances, after I delete V and W. Right? With V and W there, everybody has a two-step path among your mutual friends. They go through you guys. If you take this out, some people are still connected, but others have to kind of go the long way around you. And so the extent to which you're a bridge is the extent to which that distance gets elevated when you pull this out. So we'll call any measure like this a dispersion measure, because it's a measure of how much your mutual friends are dispersed around the edge. And you have to kind of fine-tune exactly how you do it. Some things, first of all, graph theoretic distance has the property that if removing them, put them in different components, the thing becomes infinite. I don't like having infinite terms in the sum. So I could use a 0-1 valued metric. The sum actually is a pairwise sum which has quadratically many terms and can be big just by brute force if you have a lot of mutual friends. So you could do some normalization by the size of CVW. You do a few things to fine-tune it, and then you end up with the measure we're going to end up trying out. So let's actually try it out. Let's see how good is this going to be at actually finding relationship partners. Okay, so here's the evaluation part, right? So we are sort of playing with measures, trying to do something better than embeddedness. To test it, and again, one of the things about doing this with Lars, since Lars runs the newsfeed infrastructure, we can piggyback all these analyses on just all the stuff that newsfeed is collecting anyway, and so it becomes this sort of layer that we can just put on top of all that infrastructure to evaluate it. So we're going to pick uniformly at random 1.3 million Facebook users, selected uniformly subject to the following constraints. They should declare a relationship partner in their profile. They should have between 50 and 2,000 friends to cut off the two tails of the distribution. They should be at least 20 years old for a variety of reasons, including that there are a couple known failure modes for the relationship partner field on Facebook. One is that teenage girls often say they're married to their best friends, things like that. But if you say that at least 20 years old, you steer around the sort of known pitfalls that Facebook's aware of. Okay, so for each user V, it's going to be very simple. We're going to take V, and we're going to take the network neighborhood, and we're just going to rank everybody by some measure, by a bunch of competing measures, and see how often its one guess is correct. So we'll use embeddedness, the gold standard from sociology. Dispersion, this how much you disperse your mutual friends around you. And then, of course, Facebook is collecting a lot of behavior, sort of activity-based metrics of just how much you sort of spend time interacting with this person. And if those are going to do better than graph structure, then we ought to know that, right? We should only be using graph structure if it's actually adding some value here. So what are the activity-based metrics? Well, how much you message them, comment on their content, like their content, how much you check into events with them, how much you get co-tagged in photos with them, a whole bunch of things where there's some information about your activity with them. Of all of those, the two that are most useful, so I'll stick to those two. I mean, this is in retrospect after trying them all. The two that are most useful is the number of photos in which you're both co-tagged, right? If you and this person are often standing in front of a camera getting your picture taken, then that's evidence that there's a strong tie. And secondly, less obvious to us, the number of times that V viewed W's profile in the last 90 days, right? Because it turns out when you're in a relationship with someone, you just do a lot of profile viewing and, so. Okay, so profile viewing. So good. Those are going to be the sort of, and the other activity ones are just lower down. And we're just going to ask this question. For what fraction of all users V is the top ranked W, right, the relationship partner? So I'm giving the algorithm one guess. Everybody has at least 50 friends in this sample, so uniform random guessing, which we're clearly going to beat, is going to be a 2% correctness rate. And I was certainly prepared to be happy if you ended up with, like, say, 20%, because that's like an order of magnitude improvement over the random guessing baseline. And so the first surprise here is just how high in absolute terms the success rate is, right? So dispersion, more than half of all instances with one guess, it's finding the relationship partner. Right? This actually is a measure that's really causing this thing to jump out, just the way it jumped out visually to Lars and me when we would just page through picture after picture of these things. Embeddedness, as I said, embeddedness is not bad. It's not, right? A quarter of the time, it's actually getting the right answer. It's just that you can do a factor of 2 better with a different metric. Overall relationships, I'll gradually fill in the table here. Overall relationships, dispersion is beating the best of the behavioral metrics, photo code tagging, profile viewing. And actually, this says another important thing about the importance of having the right algorithm rather than just having an algorithm, right? Because if we eliminate this this column here, and we had sort of naively asked the question, which is more useful for finding this important class of social tie, structural measures or activity measures? And we had said, well, structural measures equal embeddedness, which is sort of the default assumption in this kind of thing. Then we would have said, well, the activity-based metrics are better than the structural metrics, and we would have been wrong because we would not have had the right algorithm, right? So there's often this thing that one encounters where the question, are these features useful, is the first question, but the second question has to be, what is the right way to use these features? And you can get very different performances out of different ways of using them. A couple other things. So the structural measures do better on married than in a relationship, right? So on Facebook, you can say different kinds of relationships. You can be married, engaged, in a relationship, and then some other rarer ones. It's complicated, a bunch of the other ones. These were the 2 biggest in our data. It does better on married, which makes sense because there's been more time for the social structure to sort of form around that relationship in general. People who declare themselves in a relationship, actually, now the activity-based metrics really start doing well, and profile viewing is just doing really, really well there. Again, there is sort of, people have guesses at Facebook why this is. For example, when you're in a relationship, you don't trust Newsfeed to be showing you everything that they posted, and you want to make sure you saw it, so you just go check their profile to make sure that Newsfeed isn't trying to sort of cause trouble in your relationship by not showing you things from them. So, okay, so we've got that. It's much easier to find relationship partners for one gender than the other. That was not a priori obvious to us, as in if the user at the center is male versus if the user at the center is female. I mean, there's a mix of opposite sex and same-sex relationships here. Many more of the declared ones are opposite sex relationships on Facebook. But yeah, it's quite different. And it was not a priori obvious to us which way it should go. As it turns out, it's about 10 percentage points easier to find the relationship partner when the person at the center is male. Right? Then the partner is really standing out. I mean, again, it's sort of interesting to think about what this means, but when the user at the center is female, there are a greater diversity of people who sort of structurally play a similar role to the spouse or to the relationship partner. We can combine all this by machine learning, right? We can take all these columns and all the other columns I suppressed, all the other structural metrics that you might try, all the other activity metrics, and you get about a 70% success rate when you just put that into sort of a black box industrial strength machine learning algorithm. When it's wrong, about 35–40% of the incorrect guesses are to family members, right? So when it's not the relationship partner, it's often, or regularly, it is a sibling, it's a parent, it's an adult child, things like that. Okay, just a couple things, now that you've got this, like 5 minutes to wrap up, yeah, sounds good. These things change over time, so again, just running through, once we have this framework, we can ask for a whole bunch of other stats. So the performance, time since the relationship was reported, structural measures just get better and better as the relationship gets older, profile viewing actually falls off. For people in a relationship, actually, remember, profile viewing starts out very high, it goes down, structural measures go up. They actually cross at 12 months, right? At 12 months, somehow the structure has formed, the profile viewing has dropped off, there's this crossing point. People kept asking us, so we finally computed it. When the algorithm is wrong, there's actually a 50% higher chance that the couple will break up over the next 2 months than when it's right. So there's something in the, okay, lots of things. I wanted to pop back up to just a graph theoretic point about all of this, and then just a conclusion slide, and we'll be done. Remember that relationship partners was really a means to an end. I mean, it became a sort of fascinating question for us that connected to a large body of substantive literature in the sociology community also. But in the end, it was about what is there beyond embeddedness, right? So this picture that you've got a bunch of clusters in your neighborhood where somehow we weren't finding everything that we wanted to find. And so it suggested to us a kind of different way to look at what a network neighborhood looked like. And actually, for this, I was reminded of a talk I had gone to 10 years ago that Lotzi Lovas had given, where he made this very interesting point that lots of deep theorems in graph theory sort of have the form every graph in some class can be described by a constant number of big pieces of simple complexity plus a constant number of small things of high complexity, right? So you could sort of interpret the Semirati regularity lemma, for those of you who know that, as sort of saying that you can interpret the Robertson-Seymour graph minor theorem, for those of you who know that, as sort of saying, constant number of pieces that are simple, and then a constant amount of extra sort of complicated stuff stuck onto it. And so I had filed, and so what he asked was, and he was the one who actually asked the question, wouldn't it be interesting if we had kind of a meta principle like that for real graphs? Is there any notion that there might be a meta principle like that for real graphs? And I had filed that away, along with the Martian scientists and everything else that I was trying to keep track of here, that, it would be interesting if you could do that. And I hadn't really seen that percolate up until we got to this thing. And this is really what was emerging about these network neighborhoods, that it wasn't just that your neighborhood looks like a constant number of relatively homogeneous clusters, but it's really something extra. It's a constant number of homogeneous clusters plus a constant number of extra nodes that defy easy classification, right? So there's the relationship partner, there's the sibling, and so forth. And they're sort of sprinkled in there. Again, this is not a precise statement. It's a heuristic that worked very well for us for this particular kind of analysis. It'd be interesting to sort of ask that in a richer sense. It's also interesting, of course, that these, if this is the relationship partner and that's the sibling, they're there for very different reasons, right? Your sibling is linked to all these clusters because they encountered them at the same time you did. They grew up with you. They met your high school friends when you did. They met your coworkers when you did. The relationship partner is different. They're sort of a time traveler in your social network. You've reintroduced them into all of those things, right, through subsequent introductions. But the structural effect is sort of the same. Okay, so there's a bunch of questions. This has been one sort of look at these network neighborhoods. There's obviously a lot of other questions about, are there structural signatures for other kinds of roles? How does this relate to the way information flows through these networks? What does it mean for the original, newsfeed application of how do we prioritize content if we know all this? But I want to sort of pop back up to a higher level, right? This is sort of where we've gotten in this larger project of asking the question, what does the social network of the world look like? How do we analyze it computationally? How do we make sense of it? And how does that feed back into the computational systems that are actually modulating the information that gets shared on social media like Facebook or like Twitter? And if you think about that, it's really this kind of mapping activity of something that on the one hand is familiar to us, right? These social networks that we are intuitively very familiar with, but that we never have really seen in this way, that we've never looked at in sort of this quantitative, dispassionate, clinical sort of way. And in that sense, I'm reminded of the unease that people began expressing when social media first appeared in that sort of 2004 to 2006 time period. There were a variety of op-eds, and one that a paragraph from one of them that I was always very, very struck by is the following, saying that MySpace, back when it was the dominant social networking site in 2006, it's doubly awkward because it makes public what should be private. It doesn't just create social networks, it anatomizes them. It spreads them out like a digestive tract on the autopsy table. You can see what's connected to what, who's connected to whom, sort of evoking an earlier era in science when people first began taking scalpels to cadavers, and other people turned away repulsed, saying, don't show me that, I don't want to know what's inside a human body. And there's something going on here like that, right? That social networks are, on one hand, very familiar to us. They've been around ever since we lived in social groups. But it's really the first time that we're able to see them at this kind of high resolution, this unprecedented level of scale and resolution. And it's really this computational, mathematical, combinatorial language that's allowing us to ask questions and sort of seemingly find the right structures to describe the sort of phenomena that we see. And I think that's a very interesting ongoing activity. There are a lot of other questions around this. I mean, it's sort of hard to give a talk like this without putting down something like the third bullet about, all of these analyses are based on stockpiling huge amounts of personal data in a single place. These systems are all fueled by large amounts of personal data. And as with any complex engineered artifact, it tends to be dangerous to handle the fuel directly, right? It's a dangerous thing. And that's very much true here also. But I think the point is that if we think about these systems, as computer scientists and applied mathematicians, we're in this fortuitous position that somehow the language for talking about the phenomena that we're seeing here, although they're really very much about our everyday lives, they're inherently a computational and mathematical language. And I think there's going to be a huge opportunity for work in that area to really inform the next steps in the kinds of models, policy discussions, and applications that we take going forward. Thanks very much.